Hello everybody, welcome back to another video. This time we're taking a look at a little calculus problem, and it's the integral of the natural log of x with respect to x. Now, common problems I would see with people integrating this is they would just put the answer as 1 over x plus c, and this is wrong. You need to remember that going the other way, if we differentiate log x, or natural log of x, we do get 1 over x. So you've got to be really careful that you don't get these confused. So with that in mind, let's have a look at a nice way to approach this problem. Okay, so I've drawn some axes and we are going to draw the graph of log x. So it looks something like this, and it sort of increases. And this is the point 1 on the x-axis. Okay, great. So the approach we're taking here is if we're in the case of a definite integral. I'll get to if it's an indefinite integral in just a moment, but for now let's suppose we're trying to integrate this between 1 and 5. In other words, we're trying to find the area here, shaded in red. Right, so this is what our problem looks like. We are trying to find the area underneath the curve of log x between x equals 1 and x equals 5. So in other words, we're trying to find this red area. Now, as we stated before, this isn't the easiest integral to calculate, and here's another way of thinking about it. So usually the way we integrate a function f of x with respect to x, where y equals f of x. Okay, and it always seems like x is the integrating variable. However, we can quite easily integrate against the y-axis. The only difference is we just need to have it in terms of y. In other words, we would have a function x which equals f of y, and we would just integrate f of y dy. Okay, so let's have a look at this. So let's suppose that we have our function y equals log x, and remember what log x actually means. It's log base e of x. Okay, so how can we get this in terms of x? Well, this is easy. It's just called exponentiation. If log ex is y, then this means e to the y equals x. So what can we do now? Well, we can change this integral as follows. So we can now consider the integral e to the y dy, which is much easier to calculate than natural log of x dx. However, we have to be slightly careful because integrating e to the y gives us the area against the y-axis. Let's say we integrate from y between 0 and the corresponding y point here, so whatever this is. Well, if x equals 5, then y equals log 5, so this is natural log of 5. Okay, then this integral here is going to give us the following area. So it's the area between the y-axis and the curve. So it's this shaded region here. Okay. So I hope that makes sense there. What we've essentially done is switched around the function log x to make it easier to integrate. Right, but note, if we integrate this here, e to the y dy, between 0 and log 5, we get this blue area. And this is not what we were initially looking for. We are looking for this red area. However, we have created just a rectangle here. So it goes from there down to 5 and along to 0. Which means the length of the rectangle is just 5. And the height is just log 5, or natural log of 5. So, the area of the region we're looking for, so the area of the red region, well, this is just equal to the area of the rectangle, and I'll draw a little version here. So up the sides it's natural log of 5, across the bottom it's just 5, and we need to take away the area of the blue. So I hope you can see what we've done here. That's excellent. So take away the area of the blue, And we can calculate this nice and easy now. Okay, so this is where we're up to. So we're trying to find the area of the red still. So let's work out the area of the rectangle. Well, that's just 5 times natural log of 5. So 5 ln 5. And we're taking away the area of the blue. Now remember, this was just the integral between 0 and log 5 of e to the y dy. Now the very special thing about the exponential function is that it differentiates and integrates to itself. So we can easily evaluate this. This is 5 log 5, take away e to the y. We need to plug in y equals natural log of 5 and y equals 0. Okay, so 5 natural log of 5, take away, and then plugging in y equals natural log of 5, we're going to get e to the natural log of 5. And plugging in y equals 0, we're going to get e to the 0, which is 1. I'm just going to be careful with the minuses there. Okay. Now, knowing your log rules, e to the natural log, they're going to cancel out. So we're just going to be left with 5. And our final answer is going to be 5 natural log of 5. Inside this bracket, we're now going to have 4. So it's going to be minus 4. And that is the final answer there. So the area of the red region is just 5 natural log of 5 take away 4. So let me just summarize. So this implies the definite integral between 1 and 5 of natural log of x dx equals 5 log 5 take away 4. Excellent. Okay, now if you didn't have any limits on your integral, in other words it's an indefinite integral, then this is how we would proceed. Okay, well we'd say that this is the same as the integral of doing the function 1 times natural log of x dx. And hopefully you're familiar with the integration by parts formula, which can easily be derived from the product rule, by the way. So again, my plan with this channel is to encourage people that you don't need to memorize every single formula, okay? Because they can all be derived. As long as you know the basics and certain definitions, you can derive almost every result. Okay, so the integration by parts, what does it say? It says if we've got an integral of some function u times dv, then this is the same as u times v, where v is the antiderivative of dv, take away the integral v du. Okay, and if you want to see a video on how that comes about, then do let me know. So in this case, our dv is going to be 1 because we want to integrate it. And we already know how to differentiate log x. That's nice and easy. It's just 1x. So that is our u. Okay. So let's find v and dv. Well, v is just going to be x. Because if we differentiate v now, we get 1. And du is going to be 1 over x. So let's plug this into our by parts formula. And we're going to get, well, u times v. So that's these two. X natural log of x, take away the integral v du by dx. Well, this is x times 1 over x dx. Okay, the x is nicely cancelled, so we're just left with x natural log of x minus x plus c. And that is how to find the antiderivative of natural log of x with respect to x. So let's plug in our 1 and 5 just to make sure we were right earlier. So from earlier we did the definite integral, natural log of x dx. Well, this is now just going to be, by the work we've just done, the value x natural log of x minus x evaluated at 5 and 1. Okay, so this is 5 log 5 minus 5, and then we're taking away 1 times natural log of 1 and hopefully you know this is 0. And if you can't see why, then let's go back up to the graph. At x equals 1, our graph equals 0, so natural log of 1 equals 0. And back down here, and we're taking away 1. So what we are left with is 5 natural log of 5 minus 5 minus minus 1, which is add 1. So it's 5 natural log of 5 minus 4, which does in fact agree with our answer above. Okay, wonderful. So we've seen a nice trick to integrate natural log of x dx when we have limits. So we changed it to the exponential function, which we really already know how to integrate. And then I've shown you, using the integration by parts formula, how to find the antiderivative of natural log of x when there's no limit, so the indefinite integral. I really hope you've enjoyed this video. Please do leave a like. I hope you're enjoying the calculus videos. Please subscribe for further videos, and of course leave a comment if there's anything you'd like to see. Okay, thanks guys, see you later.